Greetings to all, welcome to the channel Simtech05. This is the second video tutorial of the quasi-static analysis. In first video I talked about increased load rate and theoretically I also talked about the mass scaling scheme. So this slide basically I explained in the previous video. If we have time event of 0 to 60 second and stable time of 1 into e raised to the power minus 8, then small increment we have to complete the simulation, and it will take some amount of computational time surely. But somehow if I able to increase that stable time from 1 into e raised to the power minus 8 to 1 into e raised to the power minus 4 or 1 into e raised to the power minus 6, then the increment size also will be increased and the simulation can be complete within the less amount of time. But for that we have to introduce some artificial mass, and once we introduce some artificial mass we have to make sure inertia is not dominant. If inertia will dominate, then it will not remain as quasi-static analysis, it will become dynamic analysis, and that dynamic condition will be also artificial because we artificially increase the mass. So basically we have some formulation, like if we have stable time increment delta t LE by C1 and increase the mass by factor of f square, make sure f square, then our stable time will be increased by factor of f. So that also I explained in previous videos, so I skipped it quickly. Basically the stable time increment is controlled by smallest element size, and to increase the stable time of the complete simulation we have few mass scaling options. Mass scaling is applicable, or we can say it's important when we have certain elements with minimum element size and we want to artificially define mass there to increase the stable time. Similarly, if we have rate dependent material, then also increased load rate technique will not work, we have to define mass scaling condition. So this edit mass scale options is available in step, make sure that is available only for explicit step, and here we have 4 ways to introduce the mass scaling. I will explain one by one each. If I talk about the reason, basically we can define the scaling to the complete model or particular set, like I want to introduce mass scaling only for few of element which having minimum size, apart from I don't want to introduce mass scaling for the other parts, other regions. Here we have other options, scaling at the beginning of a step or throughout the step. This is basically fixed mass scaling, and the second option throughout the step is variable mass scaling. So we will talk on that also. And then we have factor or target element size. Either we can define scaling by factor or by target element size. We will talk on that also. This frequency term will come only in the variable step. If you keep these options as fixed mass scaling options, then this frequency will be not available. If I say fixed means at beginning of a step, if I say variable means throughout the step. So let's talk about the fixed mass scaling. This is the fixed mass scaling as I told, and the fixed mass scaling we can define by scale factor as well as by time increment. Basically the fixed mass scaling technique introduced at the beginning of the analysis, and the same mass matrix carry out throughout the simulation, and that can be introduced by defining the mass factor manually, or we have to define the required increment size, and accordingly software will define the mass scale factor and will generate the new mass matrix that will be carried out throughout the simulation, and that can be defined for whole model or particular set. The set means element set or node set or maybe the geometric set. So there we have one example, very famous example, curve beam example. So this beam we have, this is fixed from one end and we are going to apply the displacement load here. and the first case is no mass scaling condition. In the second case with mass scaling of 16. So here we can see the strain, the equivalent strain is around 1.20, and with the scale factor of 16, the equivalent strain is 1.19. So with this much of scale factor, the results are quite accurate. And if I talk about the increment, number of increment, here 2,31,000 around, or we can say more than 2 lakh, and here the increments are just 45,000. So the difference is huge. This simulation is completed very quickly and this took little time. We will discuss on the timing, CPU timing also. So if I increase further the mass scaling 64 and 256, why I am increasing in this fashion? Because basically here we have mass scaling 0, here we have mass scaling 16. That's mean the stable time increment will be increased 4 times, and here the stable time will be increased by 16 times and 8 times, and here 16 times. But in the third and fourth cases, the results, or we can say the equivalent strain is varied, and this is not acceptable. But you don't even know whether this simulation is accurate or not if you not perform this simulation within the actual time. So, or we can say without any mass scaling or increased load rate. But then there is no sense. If we need to perform simulation in the actual time without mass scaling, then we have to compare with the scaling, then there is no meaning of such mass scaling. So to check whether those results are accurate or not, what we will do, we will always check the energy balance. Okay, so before energy balancing, check energy balancing, let's talk on the deformation pattern. See, this deformation pattern is quite similar for the first and second condition. Okay, third condition, for the third case also, here we have mass scale factor as 64. The deformation pattern is quite similar, but the fourth condition, due to huge mass in the system, inertia is dominant and the deformation pattern is not accurate. So sometime by visualization also you are able to predict whether my results are accurate or not, but many times it's not possible. So we have to check the energy. So this graph is for internal energy, and other two graph I also plotted the kinetic energy and artificial energy. Other two graph are approximate 0 for the mass scale 0. Same for the mass scale 16, the internal energy is around 60-70 e raised to the power 3, that's okay for me. But the kinetic energy initially increase, but then again it will approximate to 0. Similarly, artificial energy also approximate 0, but in third case, here the kinetic energy is quite comparable, and the fourth case, the kinetic energy just half of the internal energy for the beginning of the simulation. Okay, then it's constant, but still this result is not acceptable. So even this result also not acceptable because kinetic energy quite comparable. The quasi-static means there should not be any kinetic energy within the system. Inertia should not be dominant, and if we introduce mass artificially up to certain value and kinetic energy become higher, then this type of results are not acceptable. So checking energy is very much important for such conditions. Let's talk about those simulations like scale factor 0, 16, 64 and 256. And if I consider root of the mass scale factor, that will be 0, 16, that means 4, 8 and again root of 256, here 16. Stable time increment, if you consider this stable time increment, this is average stable time increment within the first simulation, within the second simulation, third simulation and fourth simulation. So this is basically reduce the total computation time by increasing the stable time. Here we have 4 into e raised to the power minus 8, then it become 1 into e raised to the power minus 7, 4 into e raised to the power minus 7 and so on. So the improvement is 4 times as compared to the first condition, then again improvement 2 times as compared to the second condition, then again improvement in the delta t 2 times as compared to the third condition, because if I divide 8 by 4, the ratio will be 2, and then the improvement also 2 times. Similarly, 16 by 8, the improvement 2 times, approximate 2 times. So these are total increments, as I mentioned, 2,31,000 around 45,000. These also having of ratio same as root factor. See, 4 times, approximate 4 times increments reduced, then approximate 2 times, then again approximate 2 times. And if I talk about the CPU time, I use here 20 core to perform the simulation. So they will took that much amount of CPU time, and you can see very less CPU time considered here, but those results are not accurate. So this second one we can consider as a accurate result, because kinetic energy is quite negligible here. Next is variable mass scaling. Variable mass scaling is important, we will talk, but we have to define the variable mass scaling using these options throughout the step. When you check on these options throughout the step, the first options by scale factor, this option is highlight. In the type, this option is highlight, means you cannot artificially introduce mass by scale factor. You have to define some target increment size. Okay, what is your target increment, and accordingly software decide the scale factor. So that also I mentioned here. At the beginning of the step, mass is introduced, then within some periods again the mass scale is redefined. Okay, and this period is depend on the frequency, whatever the frequency value you will give. As I mentioned, the desired minimum stable increment we have to define, and mass scaling will be considered automatically by the software, and that mass matrix will frequently improve as per the frequency that we will give here. So when to use such variable mass scaling? Most of the time we use the constant mass scaling or fixed mass scaling, but in some cases where stiffness property of the system change drastically, means most cases it happen in the manufacturing type of simulation. Say for the forming, the element distort excessively. For such cases we need to use variable mass scaling, or we can use. Again, this type of mass scaling we can use for the whole model or particular set, element set, node set, or geometrical set. Yeah, important point, when we use this variable mass scaling, we have few options here, if below the minimum target and so on. So we will talk on that. Here the first option is uniformly distributed. So basically the uniformly distributed option same as scale factor we define manually in the fixed mass scaling. What it's mean? See, in the fixed mass scaling we introduce scale factor manually, but here if I define uniform, means we have to define the target size, and as per the target size scale factor will be defined uniformly throughout the model. So basically both are the same options, but this can be used in only fixed mass scaling, and this can be used in both fixed and variable mass scaling. So as I mentioned, scale factor decided by the software. We have to define only the target increment size. User has to be defined target increment size. Then the second options, if below minimum target, means if delta t is less than the target element size on the particular number of elements, then it will increase stable time increment for those elements. And this mass scaling can be utilized for dynamic analysis also, but wherever we have the mass scaling or minimum element size, there we will get artificial mass. On such conditions, on such regions, we should not focus our result. Okay, if our result is focused on particular area where we have least element size, then we cannot do anything. We cannot utilize this mass scaling for the pure dynamic analysis. Of course, for the quasi-static we can use, but for the pure dynamic we cannot use. But if say my component is matched with some element size and we have some fewer element size due to some geometrical irregularity, but my result is not concerned on those regions, so we can utilize this for the dynamic analysis also. And last is non-uniform to equal target. This is valid only for the quasi-static, and the mass is non-uniformly distributed in the complete model to achieve a fixed target time increment. Like I want to target the increment size of 1 into e raised to the power minus 6. So if some element having very less size, so artificially the mass will be increased there, and if some element having larger element size, then maybe the scale factor is less than 1. Means uniformly mass is distributed throughout the component to achieve the target element size. So this is all about the variable mass scaling. So the last point is different type of mass scaling options like semi-automatic mass scaling. 90% time we utilize this options only, semi-automatic mass scaling. This automatic mass scaling condition is very special condition and utilized for the bulk forming type of simulations. Maybe in next video we will talk on that particular point separately. Then we have reinitialization options and disable mass scaling options. Make sure the reinitialization options is utilized when you have multiple steps, and the first step is maybe quasi-static step where you define the mass scaling. Then after, the second step is not a quasi-static step, it's a fully dynamic step and you don't want to define any mass scaling further. So what you can do, you can check on these options for the next step. Means whatever the mass system have at the beginning of the simulation, that will be reassigned to the system again, and then the second step analysis will be performed without any mass scaling. But here the disable mass scaling throughout the step is quite different options. Okay, this not mean the mass scaling is fully deactivated. It's mean if you have first step with variable mass scaling and the second step you don't want to define variable mass scaling, you want to define only the constant mass scaling or fixed mass scaling. So what will happen, whatever last mass matrix you will get from the step first, that will be carried out in the step 2, and throughout the step 2 that will remain constant. Okay, that will not modify, but still there is mass scaling. Okay, the mass scaling is constant, but still there is mass scaling. If you want to remove the mass scaling, then you have to utilize this option, reinitialize the mass. So hope you will get the idea of mass scaling. Let me show you in Abaqus also. Okay, so this is my model, the very easy model I considered here. Only this curve beam we have. Likewise, go to the standard view, then in the property I assigned material property, plastic material property with density. Make sure you have density here. So density and the elastic plastic material property. So those are the plastic points. I assign the property, then assembly step. This is only the important. Say I want to define the mass scaling for the step. Make sure edit mass scaling options. The third option is mass scaling options, and let delete this mass scaling. Basically we have this options by default, and if I want to define mass scaling for the step, you have to use the mass scaling definition and click on create, and then again the same options, semi-automatic, automatic. As I told you, this is especially for bulk forming simulations. Okay, reinitialization I will talk on that. So semi-automatic and maybe by fixed mass scaling, by scale factor. I don't want to utilize the target element size, I want to define the factor, say 100, and then simply press OK. So this is the reason whole model type by scale factor or we can say fixed mass scaling. At the beginning, sorry, type is factor. Here we can change type, like see, now type is by target increment size. So here we have target increment size. Okay, then similarly I can utilize here mass scale factor of 100. Then what is the factor value? Factor value is 100. Beginning of a step, this is the fixed step. If I utilize the variable mass scaling, like throughout the step, and target element size may be 1 e raised to the power minus 7, and uniformly I want to distribute, and frequency of, okay, in the 20 intervals, equal intervals, I want to check the mass scaling. Okay, and now click on OK. So here it will show the 20 interval, and factor is none because we don't have factor here, but the target element size we have. So this is defined. Click on OK. Now if you want to define one more step, just click on create step 2 and explicit dynamic again, and you want to remove the mass scaling. See, if you click on the mass scaling, the mass scaling is defined throughout the step and by using the previous step definition. We don't want this, we want to remove the mass scaling. So just utilize these options, click on create, and make sure you have here reinitialize mass options. Okay, what it's mean reinitialization mass means whatever mass the system have at the beginning of the step, that mass will be utilized only, no scale factor or nothing will be utilized. Okay, and now click on OK. So now we can say the first step with scale factor, or maybe by something different definition, variable mass scaling definition, and the second step don't have any mass scale factor. So performing simulation is very easy. I am not even going to perform. Let me just delete this step because I don't define loading and anything for the second step. So I define the mass scaling. Let me verify. Yeah, mass scaling and target element size 1 e raised to the power minus 6. Okay, then go to the load. Here I define one reference point and couple this age with respect to this reference point, and similarly here. And for the step, I have here the fixed boundary condition, and here we have loading conditions, and this load is this one, yeah, 40 mm of displacement in the x direction. So likewise I define the load, then I go for defining mass and go for job. The model is very easy, modeling part is very easy, only we need to understand the concept of the mass scaling. In previous video I talked on the increased load rate, and here about the mass scaling, and now click on the submit. So let's monitor and we will see. So let's start writing the simulation file. Click on dismiss and check the results. Go to the standard mode and deform mode. So in this way the deformation will be appear with the mass scaling, variable mass scaling. Actually here we use the variable mass scaling of 1 into e raised to the power minus 7 time step. So hope you are clear about the mass scaling, and thank you for listening. If you have any query or question, you can post in comment, and if you want to join community, Facebook community, Telegram community, link is available in description. You are most welcome to join there. So thank you again.